الخير جميعا. السلام عليكم. Good morning, everyone, and welcome to the second day in the FAMECSE 2022. So today we have maybe a long program. We have more than 6 speakers and 3 tutorials and our panel today. So we have a packed up program. So let me welcome our first keynote speaker, Dr. Zhen Jia. And he is the director and chief expert of the Software Engineering Application Technology Lab at Huawei, China. He will talk to us about the bridging the gap between AI and software engineering. So, Dr. Dian, can you hear us?
Yeah, I can hear you.
Okay, great. The floor is yours.
Okay. Good morning. It's my great honor to be here to present some of our research relevant to AI and software engineering. So today I would like to talk about my experience on bridging the gap between AI and software engineering. So I'm Xin Xia. I'm currently working at Huawei, China. And okay. So maybe I share my screen. I think that there's some automation is missed here. So hello. Okay, so maybe I continue. So first of all, actually, modern software engineering has accumulated a large amount of software engineering data. So, for example, in Stack Overflow, currently we have more than 23 million projects, and more than 23 million developers will use GitHub to manage their source code. And also in Stack Overflow, currently we have more than 40 million questions, and there are about 90 million questions. And also developers frequently use Git, SVN, or Bitbucket to manage their source code. And when they have some problems, they will report it in Jira or Bugzilla. And also, there are a lot of software engineering data from various companies, and each company also produces a large amount of software engineering data. So to summary, we have millions of projects, millions of bug reports, and millions of repositories. However, it's not easy to analyze the software engineering data. Consider that the software engineering artifacts are heterogeneous. So here I give you 5 examples of software artifacts we will use every day. So they are source code, development history, bug reports, code review, and software forums. So for example, source code, normally source code is structured and you can run it and correct the execution trees and you can get a lot of comments of source code. And the second example is bug reports. So in a bug report, it contains the metadata, and you can use natural language to describe the bug reports, and sometimes you attach the code or the exceptions to describe how to reproduce the bug. And there are a lot of discussions of bug reports. In these 2 software artifacts, you can find there are lots of difference. So the technology to analyze this kind of software artifacts should be different. So for this point, we can conclude that analyzing software engineering data is complex. And before I present the details about mining software repositories, so let's briefly revisit what do software engineering do every day. So normally software development process is also very complex. So as a developer, every day he needs to join various development activities. For example, he needs to do coding, he needs to design software, he needs to do debugging, and he needs to ensure software quality, and he needs to write the documents. So there's a large amount of activities he needs to join, which makes the software engineering development is complex. So considering both analyze the software engineering data is complex and the software development process is complex. So actually our core question here is whether we can or how to leverage the software engineering data to handle the complex of software development. So this is the core problems I'm working in the last few years. And to solve the problem, we need a lot of AI technologies or intelligent technologies. So before I present the details on how to dig the data, so let's briefly review the state of AI today. So for example, as a data scientist for the AI people, so he has a lot of intelligent techniques. For example, he knows a lot of statistical analysis techniques. He knows a lot of data mining. He knows a lot of machine learning. And he uses this kind of technology to find the problems in different domains. For example, he may find the problems in transportation. So he collect the data and use this kind of intelligent technology to solve the problem. And later, maybe he find another problem, for example, in operating system. So he collects the data from operating system and also use the intelligent technologies to solve the problem there. And continue, maybe he go to the domain N to solve the problem again and again. So for this reason, you can find that there are gaps between AI and software engineering. So I listed them as shown in this table. So as a data scientist, actually his knowledge of the domain is low because he knows a lot of intelligent techniques, but he don't know the details about the domain. For example, he don't know how to drive the car. He don't know how to write the good quality software. But as a good software engineer, his knowledge about the domain is high. He knows how to write the good quality for software, and he knows how to do the software testing, and he knows how to debug the software. But his knowledge of the techniques, for example, the AI technology may be limited. For example, he never thinks about how to use AI to solve different software engineering problems they match. So actually, there are some gaps. So to address the gaps, so this comes back to my research. Actually, my research is to try to bridge the gap between data scientists and the software engineer. So the idea is to build the automated tools to by mining and analyze the rich data in software repositories to handle the complexity of software development. So this is my whole research area. That is to say, you can think my research is more like the bridge as shown in this slide. So with the years of my research, actually, I found three challenges when we try to bridge the gap between AI and the software engineering. So I listed them as here. So these three challenges are easy over hard. Sometimes we need to consider the simple solution first. And also the second challenge is strong performance of techniques is not enough. And we need to have a deep understanding of the domain, which is essential for software engineering research. And the second challenge actually find is research results should be presented in a domain-centric context. That is to say, we should not directly use the existing evaluation matrix for other domains and directly use it to solve and to evaluate the performance of software engineering techniques. So these are the three main challenges I found in the years of research in AI and SE. And now I will go to the next slide to use three case studies I performed to show what these challenges are and what lessons we can learn from these challenges. And the first challenge, I named it as easy over hard. So we should consider the simple solution first. So I would like to use our ASC 2018 paper, which aims to analyze the neural machine translation-based commit message generation as an example. And so in these studies, we analyze the commit message. So we know that a commit message is important for software engineering, especially for program comprehension and software maintenance. So when developer change some code and they submit to Git or submit to SVN, they need to write the commit message. So this kind of commit messages can help maintainers or help the developers to understand why they perform this kind of source code change and also what they have done in the source code. But normally developers is lack of the direct motivation or there are some time pressure. So maybe they just randomly write some poor quality commit message, so which can be harmful for program comprehension and software maintenance. So in our research, so we propose automated commit message generation. That here to say whether whether we can automatically generate a sentence of the commit message to describe what we have done in the software change and what why we should perform this kind of change. So this is, we name this area as automated commit message generation, which can help assistant in writing high quality messages and also help replace the empty message. So actually in AIC 2017, Jiang et al., they proposed to use a neural machine translation technology to generate one sentence commit message from the diff files. So the main idea is they first collect a lot of data from GitHub, and they extract the head messages, and they perform some filter. So finally, they have like 30K thousands pairs of diffs and their message. So then they apply the attentional encode and decode model to summarize from the diff file to the commit message. So you can think that this kind of diff message is, for example, English, and the commit message may be Chinese. So the main idea is to use neural machine translation to translate the diff to the commit messages. It's like to translate English to Chinese. So this is the main idea from their study. And we named their method as NMT, and they use brute force score to evaluate the performance of their approach. And the brute force score is 31%, almost 32 percentage. So maybe you will ask whether this evaluation matrix is good or not. So let's just take a transformer as an example. So when you use transformer to translate English to French, the brute force is 41, and translate English to German, it is 28. So for this reason, because transformer is widely used by Google, so for this reason, we can think the brute force score of 32 is good enough, and it's very promising, and sometimes it can be put into practice. But actually, from their study, there are some limitations. First of all, they did not investigate the reasons behind MNT's good performance. So this comes our first research question. So we wanted to answer, why does MNT perform so well? So this is our first research question. And also from their paper, we find actually MT is complicated and also very slow. So they use the attentional encode decode model, and it takes 38 hours for training on that GPU. So in 2018, so we think this amount of time is very large. So in this case, we wanted to analyze, can we design a simple and fast approach outperform NMT? So these actually are the two research questions we wanted to analyze in our study. So to answer the first research question, why does MT perform so well? So we will go back and manually analyze the results come back from MT, the commit message generated by MNT. So we first randomly select 200 test commits from Jiang et al.'s test sets, and then we perform the human evaluation. That is to say, we manually select the commit message generated by MT, which we consider them as good messages. So then we manually analyze this kind of good messages. And actually, when we analyze these messages, we find actually 37% of the reference message of this good message actually are noisy. I give two examples here. The first one is the bot message. So give you an example here. So for example, for this commits, so they change the 2 lines of code, and the ground truth reference messages ignore updates modules, apps, and foundation portal, and the message generated by MT is also almost the same thing. Ignore update models, apps, foundation portal. You may think that the message generated by MT is excellent, but actually this kind of message is generated by the bot named the referee continuous integration tool. So in practice, if you use another tool to generate the commit message by the tool, it's actually cost limited value to the developers. So for this kind of message noisy, we named it as the bot message noisy. And also another example, we named it as the trivial message. So this is the example. So the reference message is update changelog. And if you use NMT, it will also give you the same message, updated changelog. But if you check the details of the commit message, if you just tell people the reason they change the commit is update changelog, it creates limited value to developers. So we named this kind of noisy as trivial message because it contains little and redundant information. So now next thing is we want to check the amount of the noisy message in Jiang et al.'s datasets. So we manually identified some patterns from our dataset, and we try to use the patterns to identify the amount of the noisy. So actually, we find that in the training, validation, and test sets, the total amount of noisy message is about 16%. So we can conclude that noisy messages are very common in Jiang et al.'s dataset. And then we would like to analyze the impact of the noisy commits for their datasets. So we first use their dataset, and we try to remove the noise message, and so that we have cleaned the datasets. And then we train and test MT on the cleaned datasets that here to see to remove the noisy datasets. And then we find for Jiang et al.'s dataset, the original blue force score is 32. But when we worked in the cleaned dataset, the blue force decreased substantially from 32 to 14. So that is to say the performance declined by a large amount. So we can conclude our first finding. Actually, the good performance for MNT mainly comes from the noise commits in Jiang et al.'s datasets. That is to say, they did not clean their datasets very carefully, and which caused the high performance of their datasets. And based on the first findings, so we further wanted to analyze, can we have a simple and fast approach to outperform NMT? So then we can go back to our study. So we have another finding. So we find that for almost all of the good message, we can find one or more similar training commits. So this is an example. Sorry, the slide did not have the automation now. So this is example. For example, this is a test commit in our test set, and the reference message is missing import. And the message generated by MT is add HO to hosts. But if you check the code, the diff file here, you can find actually they did add this kind of HO to hosts, the statement here. And however, if you check the training commits, you can find that there is one very similar code change. They also added the HO to hosts. So this is a very similar training commits from our datasets. So this inspires us whether we can have a very simple approach to solve the problem. And for example, we propose a nearest neighbor-based approach, maybe a nice and simple idea. So the main idea is, for example, give a new diff and also give a source code change in our train sets. So first of all, we would like to measure the similarity between these new diff and with the diffs in the training sets, and we can find the nearest neighbor. For example, the one in the training set which is most similar to the diff, the new diff file here, and then we direct output the commit message of the nearest neighbor to as the commit message for the new diff file. And so we name this approach as engine because it's the nearest neighbor generator, and also to measure similarity between two diff files. So we can use the cosine similarity, or we can use the brute force score to measure similarity. And so this is a very simple approach. And when we use this kind of simple approach to the original dataset, for example, the noisy dataset, and also in the clean datasets, we can find that we increase their brute force score a lot. For example, in the noisy dataset, the original result is 32, so we can improve it into almost 39. And also in the clean dataset, the original result is 14, and we can improve it into 16%. So also improved a lot. And also when go back to the time efficiency, so you can find for our simple approach engine, you can find there's no training time because it's just a nearest neighbor search. And for the test time, it just need 30 seconds. But for the deep learning ones, you can find that they are linear almost 30 hours and 70 minutes or 5 minutes for the training and the testing. And for the clean ones, it's also the same results. So this is our okay. So actually, we can conclude here that our simplest nearest neighbor-based approach is considerably faster than MT and outperforms NT by 16 to 21%. So this is the lessons we learned in the first example. So the first of all, we need to always think about that clean up the dataset carefully is very important. So there are lots of noisy commits will affect the performance. So when we perform software engineering research, we should be careful, and we should pre-process the data and even manually check the data very carefully. And also this year, we have another paper to discuss about the issues in the comments generation dataset. We also find this kind of noisy here. And the second thing that I would like to highlight is we need to consider the simple approach first before we apply the complex one. So first of all, actually, our nearest neighbor algorithm actually is not perfect, and because it's very simple and to be honest, it's harder to be used into practice. But if we can consider this kind of nearest neighbor algorithm first, it can help us understand how to solve this problem. And also, before we perform any other software engineering research, we need to spend some time to understand the data. And sometimes we can design a better model or better algorithm. And actually, if you check the code comment generation or commit message generation papers, they consider the nearest neighbor algorithm into their model. So some of the recent studies they combine both deep learning models and also information retrieval based model, that is the nearest neighbor based models, together to generate the good pieces of commit message or generate the code comments. So this is actually there are many follow-up studies followed by our study. So this is the first lessons we learned from our study. And the second lessons we learned is strong performance of technology is not sufficient. So I would like to use our TSE paper in 2018 as an example. So our study aims to analyze the time developers spend on measuring program comprehension. So the main idea of our study is we want to analyze this core problem: how much time do developers spend on program comprehension activities? So because from our textbook, you can find that almost all of the textbook or almost all software engineering research papers will highlight that program comprehension is an essential and time-consuming activity in software materials. And there are many studies find that this time consumed that more than half of our developers' time. Actually, if you check all of these previous studies, you can find that there are lots of limitations. First of all, actually, most of the conclusions are based on the anecdotal evidence, and they only performed the controlled experiments with artificial setting, and also involve a small number of participants, and they only consider the program comprehension activities that occurs in the IDs. So these actually are the limitation of the existing studies. So actually, we wanted to analyze this kind of well-known assumption that a program comprehension is time-consuming, because the validated this well-known assumption is very important for the follow-up studies. In software engineering, so many tools to help improve the efficiency on program comprehension. But if we find that the program comprehension is not time consuming, maybe we spend a lot of time to develop some useless tools. So this is the core problem we want to validate. So how we do it? Modern software development actually has changed the way developers develop software. For example, I'll give you an example. So developers will use multiple applications to complete a task. So suppose they find a bug in Eclipse or in IntelliJ. So normally what we should do is we try to find the solutions in Google. For example, we enter the exceptions into Google, and maybe Google will redirect you to the Stack Overflow. There would be some code or some solutions, and we test the solutions in JS Fiddle, and then we integrate the source code back to the IntelliJ, and then we maybe submit it to the GitHub. So actually, in this case, we will use a lot of applications, for example, the IDE, the web browser, and the JS Fiddle, and finally we will submit our code change to Git. And actually, for this whole process, you can find that the program comprehension activities might happen across many applications. That is to say, he might understand the code in IntelliJ, and maybe understand the content in Google, or understand the code in Stack Overflow. So this comes out the first challenge, the first issue, how to correct the interaction data across multiple applications. So we need to correct all the behavior data from this kind of applications. So the good news is to solve the problems. In ASC 2015, actually, we developed a tool named Activity Space. So when you install this kind of activity space in your laptop or in your computer, so it can use the operating system APIs and accessibility APIs to correct all of your behavior data. So this can support the analysis of your behaviors. So we can use the data collected by activity space to analyze the time they spend on the comprehension in behaviors. But this comes out to the second challenge. So these are the table. You can find the data we collected by activity space. So if you check the data here, for example, in the T1 time, so you can find his activities do some mouse click. And also you can find that he works in the Eclipse, and also his source code file is jstree.java. So from this one, you can imagine that maybe he is trying to do some navigation into the IDE. But in time Tn, his activity is the keyboard or mouse click information is Control V. And if you check the window title, you can find that he is worked in the Google search, and he entered the Java calendar. So for this reason, you can think that he might want to find some APIs for the Java calendar in Google. And so you can think he tried to search for some relevant code. But for this kind of table, how can we identify the time spent on the program comprehension activities? So these are the second challenge we met. So we try to solve this problem, and we read many other materials from psychology. And actually in psychology, they have this kind of concept named reaction time. So reaction time is mentioned by the time that elapsed between the end of a physical action sequence and the beginning of a concurrent mental process. So I give you an example. For example, when you are working in front of a computer, so suddenly, for example, in 1 or 1.5 seconds, there is no no keyboard inputs or no mouse click information. So it means actually you're just looking at the screen, you try to understand the contents on your screen. So in this case, you can see this time is used for program comprehension. So based on the definition of reaction time, so we design our data correction framework. So the main idea is on top of the framework, you can still have the activity space to correct the data. And after you have the data, so you use the idle period to split the data into different sessions. For the idle period, it means, for example, for 30 minutes or 1 hour, there's no activities. It means maybe you go to attend a meeting, or if you go for lunch or dinner or something else. And for each session, so you further split the sessions into different spreads. And you use if the interview time is larger than the reaction time, you can divide them into different spreads. And the next thing is you need to analyze the intention of each spread. So here actually we proposed a lot of heuristic rules to identify the categories of the spreads. So finally we categorize the spreads into 3 categories. The first one, you can think it's the navigation. It means that you try to navigate or find some code you want to do. And the second category is editing. It means you want to write some code. And the third one is comprehension. So it means you try to understand the content in the screen. So then we can measure the total time for in each sprint as the amount of time you spend on the program comprehension. So then we collect the data from almost 70 developers, and we collect more than 2,400 effective working hours, and we analyze the data, and we have a lot of interesting findings. For example, we find actually program comprehension do take up 58% of developers' time, and also beside IDEs, developers also use web browsers and document editors than program comprehension, and also Java developers spend more time on program comprehension than C# developers, and senior developers perform less time on program comprehension. And if a project is in maintenance phase, they need more time to do program comprehension. So these actually are the main findings by analyzing the data we collect and by using our framework. And you can find this might be very interesting, but actually we can. If we are data scientists, we can stop here and conclude the whole study. But actually, the core questions still not answered. That is to say, why does it happen? Why do developers spend so much time on program comprehension? It is still not answered. So we need to go deeper to answer this kind of questions. So we go back and we improve the study process. So this figure actually I really want to share with you when we are doing software engineering. So we should not just report the data or the numbers we have get. We also need to analyze why and the intention and the reasons. So we go back and as I showed in previous slides, you can find that we did a lot on the data collection and analyze. And actually, we continue to have the interview phase to analyze the insights we get from the data collection and analyze phase. And also, we also perform observation study to manually read how developers perform comprehension. And based on the interview and the observation study, so we have a lot of other findings. So we perform another round of in-depth analysis, and we also perform the post-study survey. And here are some conclusions we find. Actually, we interviewed 10 people. We asked a lot of questions, and there are some results. For example, also we performed the observation study. For example, we randomly choose 200 sessions which have long program comprehension times, and we also try to understand the root cause. So with 200 sessions and also interview, we actually conclude 10 reasons. Yes, takes so long time. And for example, there's no comments or insufficient comments because the source code has meaningless class, methods, variables names, and also because the large number of LOC in source code or method or because there is inconsistent coding styles, and there are many reasons. Actually, if you check the findings here, and also many of my follow-up studies try to build automated tools to solve the problem. For example, for code comment stuff, so we try to build the code comment generation tools, and also for the insufficient code comments, we also propose some techniques to update the code comments automatically. And also for the meaningless class method and variable names, you can find many studies which try to recommend the correct names. So these are some findings from our study. And also after the study, we also send back the result session and the abstract introduction session to the 10 interviews. And we also ask them for their feedback about our findings. In this case, we also collect a lot of new findings. And okay, so for this lessons, I really wanted to share with you is actually a deep understanding of the domain is essential. So we should not just end with the quantitative analysis. When we are doing software engineering research, we should perform both quantitative and qualitative analysis together. So we can have a very comprehensive understanding of the problem. We can show that we are the expert in the software engineering domain. So this is the second lessons I learned. And the last challenge is results shouldn't be present in a domain country context. So I would like to use our ICSME 2017 paper as an example to show what these challenges and what we should pay attention to. So for our case study, we try to compare the performance of the supervised and unsupervised models. So this is a brief introduction of just-in-time defect prediction. So the main idea is, for example, when developers change the code, they submit to Git. Suppose we have a developer defect prediction tool. So when they submit to Git, so our tool can predict whether their code change is buggy or not. So if it is buggy, we tell them they have the bug. If this is not buggy, so we can tell them it's clean. So this is the main idea of just-in-time defect prediction. And actually, in the last decades, so we mainly focus on the supervised just-in-time defect prediction. So main idea is, first of all, we would like to extract a lot of metrics from the heat trigger changes with no defect information. So for example, here are some metrics like the number of subsystems touched by the current change, and number of directories touched by the current changes. So these are the 14 metrics we frequently use for the just-in-time defect prediction. And then with the matrix and the heat trigger changes with no defective information, so we can build the prediction model, and then give a new change, we can use the prediction model to tell you whether the change is buggy or not. But actually in FAMECSE 2016, so there are some people, Yang et al. Proposed as very simple unsupervised defect prediction model. So they did not need to use any training data, and they just sort the defect prediction model by using this matrix, the lines of code in a file before the current change. So they sort LT from small to large, and then they find this kind of unsupervised model can detect 30 to 74% more defect introduced change than the best supervised models when inspecting 20% of LOC. And in this case, actually, we find there are lots of advantages of unsupervised models. For example, it's easy to understand, no need to label the data, and under the same inspection cost, it can find more defects. So it makes sure that our previous studies on defect prediction makes a very simple problem too complex. But their study also did not answer why do supervised model perform so well. So we need to answer this question. So to answer this question, so we need to revisit the cost-effective matrix we used in the last decades. So in cost effectiveness, it means give a limited budget. For example, in a change, you change the 1,000 lines code, but it's impossible to manually inspect all of the code you write in a release. So if you check only 20% of the code, like 200 lines of code, so how many bugs can you detect? So this is the cost effectiveness. But because of previous works on the predictive models based on the supervised learning models, so none of the previous study reports how many changes we need to inspect when inspecting 20% of lines code. That is to say, suppose you inspect 200 lines for method 1, maybe you need to check 500 code changes, but another one needed to change check 20% of the changes in a release. So it means maybe the first one can be better. So we need to analyze the number of changes inspect when inspecting 20% of lines code. Actually, we find that a supervised learning approach compared with the unsupervised learning method, unsupervised learning method can detect 60% of the bugs, but the supervised learning ones can only detect 31% of bugs. But if you check the change here, sorry, I cannot see the number here. It's about the supervised ones need to check 30% of the change, but unsupervised learning ones need change. That is to say, the unsupervised models need to inspect twice as many changes as supervised models. So this is the main limitation of the unsupervised learning model. And also, we wanted to further analyze, do unsupervised models perform better than supervised models? And so we propose two domain-centric evaluation metrics. These metrics are PCR at 20%, that is proportion of changes inspected when 20% lines code modified by all changes are inspected. So this follows well with the previous example as I shown. And the second one is RFV, we named as the number of initial false alarms encountered before we find the first defect. That is simply to say, for example, we inspect 5 changes recommended by a model. So maybe the first 4 are not buggy, but we named it. We think it's buggy, but the 5th one is correct. This is the buggy one, so we can think the IFA score is 5. So in general, the lower these values, the better the performance. So we use these two metrics to revisit the supervised and unsupervised learning models. You can find when you check the PCR at 20%, the supervised learning ones is 0.33, but unsupervised one is 0.6. And for the IFA, it's 4, but unsupervised is 70. So for 70 in practice, it's not acceptable because no one has the patience to check the first 70 for false positive to find the real buggy change. So this is the main problem for the unsupervised learning models. So actually, for this challenge, actually, I learned that actually every evaluation measure has its own bias. So we can always use some trick to change the evaluation metrics to achieve a very good performance. So to solve this problem, we really need to design the domain-centric evaluation measures, and also we need to understand why we get strong results is more important than how to get strong results. This is also very important. So we need to understand why it's more important than to understand the how. And so to summarize my talk today, so first of all, today I briefly introduce my research. My research is like the bridge, which bridge the gap between data scientist and the software engineer. And also there are 3 challenges when I find actually I try to build the bridge. The challenge we should consider simple solution first. We need to really understand the problem, and we should present our results in a domain-centric context. So this is my talk today. Thank you very much. So any questions?
Thank you very much, Dr. Tien, for the comprehensive presentation. And maybe we are a couple of minutes late for the next speaker. I think he is on stage. But maybe before we leave, if nobody in the audience have any questions, I might. Okay, so I think you have a question here. كان ممكن حد سامعه
Talking about comprehension of the program, we are using a lot of models, model-driven software engineering.
Did you hear my first part of the question? So we are using in software engineering a lot of modeling. Can you use that information to comprehend or to improve the comprehension of the program?
Okay, can you hear the question?
Sorry, can you say it again?
Software engineering modeling. So we build models, and can you use that information for the comprehension of the program?
Oh yeah, I think it's possible. And actually, in software engineering research, there are lots of studies which, for example, to do the architecture recovery, for example, to recover the architecture from the programs, and so you can understand the architecture of the software well. And also there are also many other studies. For example, they automatically generate the code comments, generate the commit message, even generate the pull requests. So for this kind of software documents, it can help you to understand why you write the code here and what is the code meaning. And also there are also a lot of other tools. For example, the code search and the code recommendation tools. We can also recommend a lot of APIs or the tools which can help you to understand the problem. So these are the tools from our country research.
Okay, thank you very much. But before we leave, maybe I will ask a quick question about the GIT that you presented in your presentation, the just-in-time prediction for the defects. So just if you can briefly give your opinion and background about the how the JET can be very useful and the what's the level of the confidence in the GIT method if we apply it in real setting in a software engineering company. So this is something that maybe more from practical perspective. So what's your take on that?
Yeah, it's a good question. So actually, when I work at Huawei, we try to deploy the different production tools inside the company, and actually we find some challenges. First thing is, first of all, we need to tell the developers, for example, when the change is buggy, but we also need to tell them what kind of bug is. For example, we cannot directly tell them there is a bug, but they need to tell them why. And so that is the developers may have less confidence about it. And also better, for example, we can also locate the lines of code which introduce the bug. So for example, I can tell you that this kind of is buggy, we can highlight, for example, line 5 may be buggy. And also maybe we can recommend some solutions to fix this kind of bug. Then the developers would be very happy to use it. Actually, we have developers and technology at Huawei, and also we get some very positive feedback from different product lines. So to summary, we should not just tell them something is buggy, but we need to tell them why, and also point out the locations of the bugs. So this can help to improve the practical usage.
Okay. Thank you very much. And again, thank you for your time and the presentation. And I think also for other questions online, or you can interact with Mr. Jen and using the platform. I think you thankfully can help us also in replying to the questions that will be posted from the audience that are attending online. Again, thank you. And now we move to our next speaker. Thank you very much.